Before we bring in a resistor, let's look at what happens with two capacitors. So let's look at capacitors in series. A battery with a capacitor 1, and then more wire, and then capacitor 2, like that, and then complete the circuit like that. What will happen? How much charge will you get? What will the potential difference across the capacitors be? Let's see if we can figure it out. Well, when you don't know what to do, think about Kirchhoff's rules. The junction rule, there's no use for the junction rule here because there's no junctions. These are in series. But we can think about the loop rule. So we imagine we're a little test charge moving along through the loop. We're going to loop this way through the circuit. We're pretty sure there's going to be current flow like that, but we don't actually need that to do the loop rule for capacitors. You'll see in a minute. Let's see, so say we loop like this. We're going from the negative side of the battery to the positive. Final minus initial, that's positive EMF. And now we know, if we assume the current is going to go that way, we know this will be a positive charge there, and we know that'll be a negative charge there. Okay, but we need to know what happens on the individuals. So what you can notice is that this wire, so the plates of a capacitor are conductors, the wire is a conductor, so we kind of have to think back to our very first week of electrostatics. This conductor is going to get polarized. It's got some positive charge on this side, some negative charge on that side. It's neutral. What's going to happen is some negative is going to get dragged up there, and some positive is going to get left there. So this has been polarized. Wow, polarized. Another thing about capacitors when you're thinking about them physically is it's always the same charge on both sides. Okay, so if this charge here has to be the same as that charge there, because that's how a battery sends out its charge, then you have to have the same here and the same here. So you'll end up with equal and opposite charge on that capacitor and equal and opposite on that capacitor. What's interesting is one plate came from the battery and the other plate came from polarizing this middle conductor, essentially. Okay, so I said all that just to let us think about the loop rule. Okay, so now if you're going along, your test charge going along, and you go from here to here, you've gone from high potential to low potential. So that's going to be a negative potential difference. What is that potential difference? We could call it delta V1, meaning the voltage potential difference across 1. But why don't we go ahead and put the formula? What is the voltage difference, the potential difference across a capacitor? It's the charge over the capacitance. So we could say, let's think about how much charge built up here. Q1 is Q1 over C1. So there's the potential drop there. And you go further, and it drops again, because this side is low, but this side is high charge, like that. But the whole thing is at the same potential. Yes, a conductor has to be at a constant potential, even if its charge has been polarized. It's still at a constant potential. So it's going to go from what here would be high down to even lower, so it's negative again. So again, minus is the charge on the second one over C2, the capacitance of the second one, and then you're back to 0. So that's the loop rule. Go around the loop, and all the differences have to be 0. Sorry, I'll edit that out. Let's see, so that's the loop rule. So let's see, what do we do with it? Okay, so now, remember before we thought about how the battery doesn't really know what's going on. So let's see, what does the battery say? The battery says, I can't see the circuit, I don't know, I'll just send out as much charge as I feel like. What does the battery feel? The battery feels the equivalent capacitance. Okay. The battery just senses that there's capacitors out there. It's good. It sends out some current, the potential, opposing potential immediately goes up. Oh, it must be capacitors. How big and where, I don't know. It just feels like capacitors. So this is all the battery knows. So we can write one more equation from the battery's point of view, which is that the Q total that it sends out is equal to the equivalent capacitance, which is all it knows, times the EMF. which is the potential it puts out. So if we use that, then we can start substituting around with this thing a little bit. Let's move the negatives over here and draw lines. You can see that we're doing a new column here. Is that the EMF equals Q1 over C1 plus Q2 over C2. Now the EMF we could write in terms of the equivalent capacitance. So that's where we're headed, by the way. We're trying to say what is the equivalent capacitance of these two. So we'll say the EMF is Q total over the equivalent capacitance. Then we can also realize Q1 equals Q total. Whatever charge flowed out of here, it all flowed to that top conductor. So that's got to have Q total on it, and therefore that's going to suck Q total here. So it's Q total over C1, Q over C1, and then what is Q2? Also has to be Q total because that's what flows out of here. It's not half. When I say a battery Q total flowed out, Q total went here positive and here negative. So plus Q total over C2. Right, and maybe you can see what's going to start to happen is that capacitors in series add like resistors in parallel. They're opposite like that. That's how you add two capacitors in series. You add their inverses and then you flip it over at the end. And if there were 3, it'd be plus C3. If there were 4, plus 1 over C3, plus 1 over C4, blah, 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 blah. So that's how capacitors in series add. They do the opposite of resistors. Can you guess how capacitors in parallel are going to add? Hard to predict.